Yeah.
Going.
All right.
Hey, fix your eyes.
Okay, so what I just showed you was this nice idealized program. Everything's at right angles. There's no resistance in the wires. Everything works every time. You can clearly see if things are connected and bulbs light up. And so when you actually go to build circuits, though, it just gets messy. Okay. So what option you can do is you can have this. It's called a circuit board. Okay. And this is like what exists like within your phones or any electronic device. Okay, so circuit boards, it's typically called like an integrated circuit board. So this has like different resistors, 10 ohms, 51 ohms. Why it has 51 ohms, I don't know, 51's a random number. And they also have like 68 ohm resistors. So, and then you have like capacitors, and then you have some really, really big resistors of like 22,000 ohm resistors. So the cool thing, and you have to be a real hardcore electronic junkie to know this. But when you look at resistors, there's a 4-band system that they use, and the colors tell you the value of the resistance. And so if you look at like these 10 ohms, it's like red, black, brown, gold, and notice those are the same. But then when you go to the 51 ohm, then it's like green, red, black, and gold. And so if you're going into like electrical engineering, you're going to take a class on nothing but circuits, okay? Called circuit theory. You might have to have circuit theory 1 and circuit theory 2. And so if you're really hardcore, like you know what the colors means. Like you can look at the colors and go, oh, this is a 10 ohm resistor, and this is a 5 ohm resistor. You got to be really hardcore to know. Oh, show them the resistor, and I'll tell you what the resistance is like.
So you're the biggest one.
Huh?
The yellow one right there, is that the biggest one?
No, that's a capacitor. That's a 10 microfarad capacitor. Okay. So what I've got here, and to show the difference. So let me disconnect this bulb on here. So I'm going to close this, okay? And we've got flow. Okay? So I've got.
Oh, we lost it.
No, we got it back.
Okay.
So we've got the source of the battery. So we've got a negative and positive side. So the electrons are flowing through. They're gaining that energy. They're going. So this path. So I've got like the positive side here and the negative side here. So in Ben Franklin's world, the positive charges are going through here. They're going through the resistor, through the switch, to the light bulb, over here to the ammeter. Now, right now the ammeter is hooked up in what we call series. You can have things hooked up in series. You can have things hooked up in parallel. So when something is in series, what that means is that it is an integral part of the circuit. So because that ammeter is hooked up in series, if I disconnect this, light bulb goes out. So if something's in series and you lose any part of that, the whole circuit goes dead. Okay?
There's a second right here.
Hold on. Okay. Now, so typically in the old school, amp meters are always hooked up in series. So basically, this is showing we got a pretty low amp. We're at like 0.5 amps right now. It's a pretty small number. So what that is, if you want to visualize this, this is like a wheel. So inside of here, there's a wheel, and it's measuring how many electrons are flowing through. And the more electrons flow through it, the higher your amps, okay? Because that's a function of time. It's coulombs per second. So amp meters are always hooked up in series. Now, in contrast to that, we have a voltmeter. So the voltmeter is connected in what we call parallel. So if it's in parallel, basically, if you envision this as being like a river. So we're going to divert some of that flow, and we measure the voltage across 2 points. So like I can take this, and I'll put go on. So what you do is the vocabulary is you measure the voltage drop. So I can measure the voltage drop across. And by the way, if you ever hook up a voltmeter and it goes negative, just switch your leads around.
We should always rate that as positive.
Okay, so right now the voltmeter's hooked up and I'm at about 2 volts, okay? So what that tells me is the voltage drop across that resistor. Now I can do the same thing. I can come over here and I can measure the voltage drop across the battery.
Wow.
Now, you'll notice that because this is hooked up in parallel and not in series, if I disconnect it, nothing happens to the light bulb. It's still going strong. So now if I do this, so the voltage drop across the entire battery
Like upright.
is at about 7. Okay? So what that means is that if I look at the sum total of all the voltage drops across, because I've got a resistor, I've got my little LED light. So this, what the battery is telling you is basically how much food is getting put out. That's your voltage. Then that tells you, hey, where's that food going to get dissipated as it goes through the circuit? Hey, I'm going to lose some in the resistor. I'm going to lose some of it going through the bulb. So that's if everything is in series. So if it's in series, if I disconnect any port, any point along there, disconnect the switch, whatever happens, okay, the whole thing goes dead if it's in series. Now, I think I might have toasted my LED light. I might have to hold on. Problem with LED light is you get burned out if you put too much current. Now, the other thing with LED lights, there's a short side and a long side to them. LED lights only work if electricity flows in a particular direction. Right? So that's why they have the short and long side of that, because, oh, okay, this will only go in one direction. So, yeah. So here's the other problem when you're actually dealing with the reality of this stuff. You can hook it up, and then, okay, great, works. Now, if that didn't come on and you're working with LED lights, so like let's say for example I switch this up and I turn that thing around.
Just blowing up.
No, it just basically blocks it. So if I turn that around, even though I have a complete circuit, there's no electricity flowing because that LED light only allows that to flow in one direction. So this is the problem with when you're actually dealing with circuits. Like, okay, you think you have it all set up, and nothing happens. Like, is there a bad connection? Do I have the LED light not installed correctly? Do I have the wires not making a complete circuit? So the beauty of the program is that it's wonderful, and it works, but it doesn't actually, like, the frustration doesn't match the frustration of actually dealing when you actually build a circuit. Let me put this back. And
different colors of lights like require different amounts of energy.
yeah. So this is a complete circuit. I disconnect anything, everything is in series. Now, up there, I'm going to connect a red light, and the red light okay. Now, the red light is now in what we call parallel. So imagine that the electricity is coming here and it's hitting this point. Now it has to split between the two of them. So it has to feed the blue light and it has to feed the red light. Now,
So it makes it more dim.
now an interesting thing happens. So this is my amps. This is my current. So right now it's at about 0.5. It's a pretty small number. When I connect the red light to it, my current goes up because it has to supply electricity to both the red and the blue light. So when you hook up things in parallel, the more things that you hook up, the more amperage, the more current that has to flow through it. So when I was teaching electricity in Africa, this is how I would explain this. And I would ask the kids, does your mom cook in parallel? And they go, teacher, what does I do? I said, so imagine that you're the only child. You're the only one at home, okay? And you're getting all of the food, okay? Nice. Now, it's Christmas. Let's say your older brother happens to come back home, okay? Now, if your mom cooks in parallel, then more food is going to flow out of the kitchen because she's going to feed you and the sibling that came back for Christmas.
Cuts the rations.
No. Everybody still gets the same amount.
Oh, okay.
But what's going to happen to what's going to happen to the rate at which the food is going to be depleted in the kitchen? Yeah, you're going to run out of food faster because you got to feed the older sibling and you. Okay? Now, eventually we're going to get into this concept of resistance. If your mom cooks in parallel, everybody's happy because everybody's getting the food. But she's going to run out of food. Okay? Faster. But the resistance is going to go down. It's because you're not fighting with your older brother for the food. So you and your brother are going to get along okay because everybody's cool, right? Everybody's getting their fair share of the food. Now, if your mom cooks in series, she's going to keep the exact same amount of food flowing out, but you and your brother are going to have to fight for the food. Okay? So what's going to happen to the amount of food you're going to get? It's going to go down, right? But what's going to happen to the resistance with you and your brother? It's going to go up because now you're fighting for the same amount of food. So this is how you can tell, but the food lasts longer. Okay? So that was the question. Like, does your mom cook in parallel or does your mom cook in series? Both have their advantages. Okay? Resistance goes down if you cook in parallel. Now, has anybody in their house ever had a situation where, like, you throw a breaker in the house and the house goes down? Okay. So let me ask you this: do you think your house is wired in series or in parallel?
Parallel.
Why?
Because one part of the house goes down, the whole house doesn't go down.
That's right. If your house was wired in series, yeah, you lose one light bulb, the whole house goes out.
Oh, no.
Okay? That would be bad. Okay?
Wait.
Welcome in the chamber.
Now,
Let's listen to the professor.
but this is how you can also tell that your house is wired in parallel. So, if you look at what happened when I put more and more light bulbs, the current goes up. So, your breakers in your house are typically rated like an amp, like 15 amps, 20 amps, something like that. And if it exceeds that capacity, the breaker throws. So, let's say that you have a coffee pot going and an iron and a blow dryer, whatever, okay? And you're running all these things in parallel. So as you draw in parallel, and if you put you're trying to run more and more things, what happens to the amount of current flowing through the house? It goes
Up.
It goes up because everything has to be fed,
Yeah.
right?
See.
So more and more current is going to flow through that breaker. If you exceed that limit,
It's like,
the
I've had
breaker
enough of
throws,
those.
and that part of the house goes out. Okay, got the visual.
I think so.
Okay, all right, back we go.